Look at the abstract vector space on the left. By itself, it's a set of objects with no concept of distance or shape. To measure angles or lengths in a space, we have to build the rules of geometry from scratch using algebra. We do this by defining an inner product, a generalized version of the dot product that takes two vectors and outputs a single scalar number. While many modern texts use angle brackets, Hoffman and Kunze use parentheses with a vertical bar. This operation turns a standard vector space into an inner product space. For an operation to qualify, it must follow three golden rules. First, it must be linear in the first argument. Second, it must have conjugate symmetry. And third, it must be positive definite, meaning the inner product of a vector with itself is always positive, unless the vector is zero. Pay close attention to conjugate symmetry. If you're working with complex numbers, the order of your vectors matters. Swapping the inputs means you have to take the conjugate of the result to keep the math consistent. These three algebraic rules are the only tools required to generate the concepts of length and angles in a space that has no physical form. With an inner product, we establish the norm, or vector length, the square root of a vector's inner product with itself. Distance is the norm of their difference. This also gives us orthogonality. Two vectors are perpendicular if their inner product equals exactly zero. Because these definitions are algebraic, they apply to any data structure that fits the vector space rules, from multidimensional matrices to continuous functions. Let's test orthogonality in a complex space, with vectors 1i and i1. Multiplying the components requires the conjugate rule for the second vector. The calculation becomes 1 times negative I plus I times 1. The result is 0, proving they are orthogonal. Now for an active recall test. Pause the video and find the norm of the vector 3, 4 using the standard inner product. Then find one vector that is orthogonal to it. The norm is the square root of 9 plus 16, which is 5. For orthogonality, a vector like negative 4, 3 works because the inner product calculates to 0. Without the conjugate rule in complex spaces, a vector's inner product with itself could result in an imaginary number or a negative value, making the concept of length mathematically impossible. To keep measurements consistent, we rely on the Cauchy-Schwarz inequality. It guarantees the absolute inner product never exceeds the product of the vector's lengths. This relationship proves the triangle inequality, confirming that a straight line is the shortest path, and ensuring abstract distances behave predictably. These theorems function as logical checks. They prevent abstract models from producing impossible results, like a shortcut that is somehow longer than the original path. To recap, inner products translate geometry into algebra, providing the formulas for length, distance, and orthogonality. This geometric framework is required before you can move on to more advanced topics like orthogonal projections and the Gram-Schmidt process. Essentially, inner products provide the coordinate system for abstract spaces, allowing us to use spatial logic to solve problems in higher dimensions. If this helped you visualize the math, please like and subscribe. We'll be diving deeper into the Hoffman and Kunze text in the next lesson.